A team of scientists has shattered a core law of life, discovering deep-sea rocks that generate pure oxygen in total darkness, tripling oxygen levels within 2 days. These natural ocean batteries are packed with $10 trillion in battery metals, and they could reshape our future if they survive. But China's race to exploit this fragile system is about to trigger an environmental catastrophe the world cannot reverse. How did we miss the warning signs at the bottom of the sea? At depths beyond sunlight, a cluster of polymetallic nodules rests on the seafloor, their surfaces bristling with hidden energy. In a sealed chamber, scientists recorded a surge. Oxygen levels tripled in just 2 days, defying every textbook on life in darkness. The numbers on the monitor kept rising, not falling. The only variable was the presence of these metal-rich rocks: cobalt, nickel, copper, manganese, each nodule no larger than a potato, yet older than humanity itself. Researchers set out to measure what was happening at the atomic level. Electrodes pressed to the nodule surfaces revealed an electrical potential of nearly 1 volt, strikingly close to the voltage of a AA battery. In laboratory tests, when 2 nodules touched, the voltage climbed higher, approaching the threshold needed to split water molecules. This was not a chemical trick or a fleeting reaction. It was a steady current, produced by the natural arrangement of metals within the nodule, driving electrons through the surrounding seawater. The experiment design was simple, but the implications were profound. Seawater, nudged by this voltage, began to break apart. Hydrogen bubbles were expected, but not directly measured, while Optity sensors confirmed a steady rise in dissolved oxygen. Control chambers without nodules showed nothing, no oxygen spike and no unexplained signals. Even after sterilizing the chambers to rule out microbial activity, the oxygen still climbed. The only explanation left was electrolysis, powered by the nodule's own internal circuitry. Lead researcher Andrew Sweetman described the moment as watching a law of nature bend in real time. He recalled that they saw an enormous amount of oxygen being produced on the seafloor in complete darkness. The voltage readings, just under 1 volt, were not a laboratory artifact. They were measured directly from nodules collected at 4,000 meters. Each metal played a role: manganese forming the outer shell, cobalt and nickel creating the charge separation, copper acting as a bridge for electrons. These elements, in the right proportions, turned the rock into a natural battery, quietly splitting water molecules for millennia. In the field, benthic chambers were deployed again and again across the Clarion-Clipperton zone. The pattern held. Wherever nodules clustered, oxygen soared. In some tests, levels increased 3-fold in 48 hours, an effect that could not be explained by any known biology at that depth. The process was silent, invisible, but relentless. Electrodes confirmed the current, sensors logged the oxygen, and the data left no room for doubt. Under the pressure of 4 kilometers of ocean, the seafloor itself was alive with unseen voltage, feeding oxygen into a world without sunlight. This delicate balance depends on the nodules remaining undisturbed. Even a slight disruption could break the circuit and end the oxygen flow. Yet as the world's hunger for battery metals grows, these natural power plants face a threat no previous epoch has posed. The next section will confront just how fragile this system truly is. A single nodule, resting on the abyssal plane, grows less than 1 millimeter every million years. This pace is so slow, it outlasts the rise and fall of civilizations, the drift of continents, even the evolution of entire species. The metals that give nodules their charge, cobalt, nickel, copper, manganese, accumulate atom by atom, layer upon layer, as seawater cycles through the deep. Each nodule is not just a battery, but a geological artifact, shaped by forces that operate on a timescale almost impossible to grasp. In the Clarion-Clipperton Zone, nodules lie scattered across a region the size of Western Europe. Some fields are dense, with dozens of nodules per square meter, while others are sparse or buried beneath drifting sediment. Every nodule exposed to seawater is a potential site for dark oxygen production, but the actual coverage is patchy, and the process depends on direct contact with the water and with other nodules. If a crawler or dredge disrupts the surface, even briefly, the circuit breaks. The oxygen stops. No technology exists to restore a nodule once it is removed. With a growth rate of about 1 millimeter per million years, even the thinnest layer lost is gone for hundreds of human lifetimes. Attempts to model the global impact of this oxygen source run into a wall. The numbers are unknown. Researchers can measure spikes in sealed chambers, but scaling that up to the vast, uneven seafloor is a challenge with no clear answer. The fraction of Earth's oxygen that comes from these silent batteries remains a mystery. It could be negligible, or it could be essential. Nobody can say for sure. What is certain is the fragility of the system. Nodules are not renewable on any timescale that matters to humanity. Once scraped away, their electrochemical function vanishes. The oxygen they produce does not return. The circuit is broken, perhaps forever. In a world racing to electrify, the metals inside these rocks are coveted, but their true value may be far greater than any market price. The abyssal plain has no defense against machines designed to harvest, in months, what took nature millions of years to build. The uncertainty is as stark as the threat. Scientists debate the scale of oxygen flux, but all agree the loss is irreversible. The world's appetite for battery metals is set to explode, and the slow, ancient growth of these nodules stands in sharp contrast to the speed and scale of the coming extraction. The next phase is not a question of if, but how fast the destruction will unfold. Global demand for electric vehicle batteries is on track to double by 2040, and the numbers driving this surge are staggering. Buried beneath 4,000 meters of Pacific water, the Clarion-Clipperton Zone holds a mineral reserve valued at up to $10 trillion. The resource is not theoretical. These polymetallic nodules contain enough cobalt, nickel, copper, and manganese to supply generations of battery factories. For companies like the Metals Company, this is more than a windfall. It is the answer to the world's hunger for clean energy metals, and the timeline is accelerating. The Metals Company has staked its future on the promise of commercial mining by 2026. Their plan reads like something out of industrial science fiction. Fleets of 200-ton crawler vehicles, each the size of a small house, will trawl the seafloor, vacuuming up nodules and pumping them through kilometers of riser pipes to waiting ships above. The scale is unprecedented. One collector can haul up to 250 tons of nodules in a single load, and the company projects continuous operations across thousands of square kilometers. The financial pitch is simple. Extract metals at a fraction of terrestrial costs, sidestep the instability of conflict-prone sources like the Congo, and feed the world's battery boom for decades to come. Investors are watching the clock. Battery metal prices have whipsawed in recent years, driven by shortages and supply chain shocks. Cobalt, for example, is essential for high-performance batteries, but 70% of it now comes from the Democratic Republic of Congo, where labor abuses and political risk threaten every shipment. The Metals Company's spokesperson calls the nodules battery rocks, nature's answer to the looming shortfall. If mining starts on schedule, the company claims it can supply enough nickel and cobalt to build over 280 million electric vehicles. That figure alone has drawn in automakers, tech giants, and hedge funds, all betting that whoever controls these metals will control the future of transportation. The International Seabed Authority has issued 31 exploration contracts for polymetallic nodules, spanning 1.3 million square kilometers of the Pacific. 40 applicants are now waiting for the final green light to move from exploration to full-scale mining. The industry is racing to lock in claims before regulations change or moratoriums take hold. Every delay threatens to leave billions on the table, and every permit granted tightens the countdown to extraction. Beneath the urgency lies a simple calculation. The metals locked inside these nodules are worth more than the GDP of most nations, and the world's transition to electric vehicles depends on unlocking them. As 2026 approaches, the pressure mounts, not just for companies and investors, but for the fragile ecosystems that have quietly powered the deep ocean for millions of years. In November 2020, the Fendouzhe submersible slipped into the Mariana Trench, its titanium sphere carrying 3 crew members deeper than any Chinese vessel had gone before. On its 8th dive, Fendouzhe reached 10,909 meters, the floor of Challenger Deep. Each descent marked more than a technical milestone. Engineers in Qingdao monitored the sub's robotic arms as they sampled polymetallic nodules and mapped the abyss with sonar and high-definition cameras. Data streamed to China's National Deep Sea Center, now home to the world's largest archive of Hadal research, including over 5,000 newly sequenced genomes, 85% previously unknown. These are not just scientific discoveries, they are blueprints for patents, for leverage, for a new kind of power. Across the Pacific, the United States is pushing for its own claim. The Bureau of Ocean Energy Management has opened 143,595 square kilometers of the Mariana region for commercial mining leases, an area larger than many countries. But the move has triggered fierce resistance from the Commonwealth of the Northern Mariana Islands. Local leaders warned that mining would devastate ancestral fishing grounds and fragile ecosystems, calling it a new wave of colonialism. Their protests fill virtual town halls and petitions, urging the United States government to reconsider. For the Commonwealth of the Northern Mariana Islands, the ocean is both sustenance and heritage. The prospect of industrial crawlers scraping the seafloor is not just a policy issue, it is a threat to survival. The contest is not only about who extracts minerals first. It is about who controls information, technology, and the rules beneath the waves. Fendouze's dives are demonstrations of state capability, deploying, recovering, and monitoring in conditions few can match. The sub's sensor arrays and communication links could serve more than science. In theory, they could track undersea cables that carry global financial data or map infrastructure critical to communications. The ability to operate unseen at such depths is a strategic asset, blurring the line between research and surveillance. The United States, meanwhile, is racing to close the gap. Leasing the Mariana region signals intent, but American technology lags behind. American companies are developing their own mining crawlers and deep-sea vehicles, but none have matched Fendouze's reliability or reach. The regulatory framework is also incomplete. The International Seabed Authority has yet to finalize exploitation rules, leaving national interests to fill the void. Regional resistance is mounting. Commonwealth of the Northern Mariana Islands leaders find allies across the Pacific, from Fiji to Papua New Guinea, where calls for moratoriums grow louder. Decades-old mining scars serve as warnings. As governments and corporations maneuver for advantage, the deep sea remains largely ungoverned. The scramble for polymetallic nodules is no longer just about supply. It is about who decides the fate of ecosystems untouched for millions of years. The stakes now reach far beyond metals. In 1989, a research vessel dragged a heavy metal plow across the Peru Basin, carving parallel scars into a once living seafloor. Scientists called the project Discol. The intention was to mimic deep-sea mining and observe what happened over time. When researchers returned decades later, the tracks were still there, barren, gray, and lifeless, cutting through the sediment like fresh wounds. Cameras lowered to the bottom captured the same pattern. Nothing had grown back. Not a single nodule, not a trace of the dense animal life that once covered the plain. The scars had outlasted generations of scientists. A field ecologist standing over the latest survey maps described the feeling as like returning to a forest clear-cut that never healed. The sediment, once home to thousands of species, had been churned into a sterile slurry. Plumes of fine particles drifted for kilometers, settling in a layer that smothered filter feeders and buried the last fragments of nodule. Microbes that drive nutrient cycles, vital for everything from worms to fish, were wiped out in the plume's path. Even now, oxygen levels in the scarred tracks remain lower than in untouched areas, a sign that the deep-sea battery has been unplugged. The Discol experiment proved that disturbance is not a temporary setback. After nearly 40 years, the ecosystem remains broken. The loss is not measured in months or years, but in lifetimes. Every nodule removed, every plume unleashed, is a permanent erasure of a system that took millions of years to build. The evidence is written across the seafloor, a warning that the harm from mining is not just theoretical, it is already real, and it does not heal. Methane, trapped for millennia beneath deep-sea sediments, represents one of the planet's largest untapped carbon stores. Estimates range from 500 to 2,500 gigatons of carbon locked in hydrate deposits, quantities that dwarf all known fossil fuel reserves. Methane released into the atmosphere is 80 times more potent than carbon dioxide over a 20-year span. Even a 1% escape could rival decades of global fossil fuel emissions. But the risks do not stop with greenhouse gases. Natural capital losses are already being tallied. Planet Tracker warns that more than $500 billion in value, fisheries, carbon sinks, and ecosystem services could be wiped out by deep-sea mining. In 2024, financial institutions controlling 3.8 trillion euros in assets joined a growing moratorium, citing unquantified environmental and economic risks. These are not abstract numbers. They reflect the food on plates, the stability of coastal economies, and the resilience of ocean systems facing unprecedented disruption. Yet as the mining countdown accelerates, the legal framework remains unfinished. The International Seabed Authority, tasked with governing extraction beyond national borders, has not finalized an exploitation code as of January 2026. 40 contractors await a rulebook that does not exist. An ISA spokesperson admits that we are in uncharted waters and that the science is moving faster than the regulations. Scientists add their own warnings. A deep-sea ecologist cautions that the full consequences of disturbing methane hydrates and nodule fields are unknown. She warns that we are conducting the largest experiment in ocean history without a control group. The absence of binding rules, combined with the scale of potential loss, leaves the fate of the deep ocean hanging in the balance. Right now, the fate of the deep ocean is being decided in boardrooms and on the seafloor, not in public view. As mining crawlers prepare to erase ecosystems older than humanity, no law or technology can restore what is lost. The world stands on the edge of a decision that cannot be undone. What we choose next will echo for millennia. Join the conversation. Your voice matters more than ever.